Today, what we want to actually talk about is integration by substitution. Yesterday, we started building an intuition about how integration by substitution works, the things that we want to look for, an inside function and the derivative of the inside as a factor. So an inside function g of x and the derivative of the inside as a factor, because that's going to be the marker that the thing we're integrating got differentiated using the chain rule, and integration by substitution is the anti-chain rule. What we want to do today is take that intuition of the things that we're looking for and build a method out of it. So we're going to build some, practice some symbols that we can write so that we can do integration by substitution. So that when we're suspicious that something might be a substitution problem, we can apply the method and see if it's working or not. That make sense? All right, let's go. So in this integral, I've clearly set this up as with g of x inside the function f of x, or f prime of x. This is the one that we're going to be integrating. So yesterday, I think we were doing like sine cubed of x. So sine was the inside function, and it was sitting inside the cube function. So here's our inside function. This is what we're going to do with it. Just like before, we're going to say our inside function. And we're going to give it a name. Most of the time on the internet, you see U substitution. And then those same people go around and use U in integration by parts. I find that really annoying. So I decided what's twice as good is to use W substitution. So we're going to name the inside W. And that's going to be g of x. Once we identify the inside, g of x, we need to make sure that our substitution is going to work. What will make the substitution work is that the derivative of the inside is a factor in my integral. So I'm going to take what I'm calling the w and find the derivative of the inside. And so then I need to look at my integral again and say, do I have g prime of x as a factor? And if the answer is yes, then we get to use substitution. We get to continue with our plan. Things are working. I need to play a little bit of a bookkeeping game here. Notice that I wrote g prime of x times dx. I wrote both of those factors in this light blue color. So what we're going to do is I'm going to take my derivative, dw dx, and I'm going to move the dx onto the other side. I'm going to play a little bit of differential sleight of hand, nothing up my sleeves, multiply both sides by dx. There's nothing fancy or tricky going on here. I just want g prime of x dx to be replaceable with dw. While we're doing this, once we decide that we're going to do substitution, we should go back to our integral and think, what is the function that we're actually going to be integrating here? What is the outside function? That's the f prime. So we're not going to write this part down all the time, but in our mind, we should always be like, aha, if my inside is g of x, then the outside function is f prime of w. That's the thing that we're actually going to be integrating. So then I go and make my substitutions. F prime is going to stick around because that's the outside function. That's the function that we're actually integrating. So I say, now I'm going to write my new integral. It's going to be the integral of f prime of w and the g prime of x dx, all that gets replaced with dw. once we do our substitution, we have to make sure that all x has been replaced with w's. All the x's have to be replaced with w's, including the x and the dx. That's why I want to lump the dx in with the g prime of x, so those two factors together can become the dw. Now we're just integrating f prime of w dw. And so that gives us f of w plus c because we integrated. And then we have to replace the w with what w represents. And then that will be the end. That will be our answer. So the substitution game means all x must become w. The other thing to remember is that we're doing differentiation and integration. If we don't have g prime of x exactly, what we need is a constant multiple in our original integral. We just need a constant times the g prime. So here's going to be our method. You make w equal to the inside. You calculate dw by taking the derivative of what you decided is the inside. And then you're going to make sure that that g prime of x is somewhere else as a factor in your original integral. How's everybody okay? Let's take a function that we have already integrated and see how the method will show up. So one of the things that we've already integrated is x squared times the sine of x cubed. As you'll see, I'm already cheating a little bit by color coding the pieces. But when we look at this function, x squared sine of x cubed, the only thing that stands out as being inside another function, the only composition of functions that we see is sine of x cubed. This x squared is not a composition with the sine or with the x cubed. It's just included with multiplication. X squared is a factor. This is a sine of x cubed. That's a composition. And then we have multiplication by x squared. So our only option for an inside function is an x cubed. So that's what we're going to say is w. We're going to start with w is x cubed. We have made our choice. Now we need to see if it's going to work. W is x cubed. That means the derivative of w, dw, is 3x squared dx. That means I need some constant multiple of 3x squared dx as a factor in my original integral to make this substitution work. I look back at my original integral, I've got an x squared dx, and that's what I need. That's the structural part of what's going on. This 3 in front of the x squared, that's a constant factor, and I can just divide that out. Here's what it looks like if you're going to try to do the problems the way that I think about the problem. I look at my integral and say, I need to replace this x squared dx with the dw. But 3x squared dx is 1 dw. So I'm going to divide both sides by 3. I'm going to say, I'm going to adapt this to fit what I have. So I'm going to replace x squared dx with 1/3 dw. Now I can start making my substitutions. Oh, there's one more thing that we should do. Since we're new, we should say, well, if I make this substitution x squared, this x squared and the dx, it's going to be replaced with a third dw. What's left is sine is going to be the outside function. So what we're actually integrating here is sine. So our integral, our outside, is sine of w. I know it's weird to introduce the outside as y, but I'm thinking of the Leibniz version of the chain rule. dy dw times dw dx. But that's the outside function. That's the one that we're actually integrating. Let's move forward and make our substitutions. So x squared and dx gets replaced with a 1/3 and a dw. The function that I'm integrating is sine. That sticks around. X cubed gets replaced with w. Now I have an integral in just w. All the parts, everything corresponds. I've got sine of w. X squared dx is all replaced with 1/3 dw. X squared dx is equal to 1/3 dw. Now we can integrate sine of w. The thing that we're supposed to get out of substitution is an easier integral, less stuff going on. What's really going on here? Sine of w. The integral of sine is negative cosine. Plus some constant. This is still in terms of w. And the other thing that's still there is the 1/3. 1/3 is now just a constant factor. It just tags along. And then the last thing we have to do is go back to x. So our final answer will be negative 1/3 times the cosine of x cubed plus c. Any questions? The place where we decide that this is going to work or not happens right here when we figure out what dw is equal to. We say dw is 3x squared. Do I have a constant multiple of 3x squared dx in my original integral? And the answer is yes. That's what told us that substitution is going to work. It's really important not to just try to like blindly wander through the process, but understand what we're looking for in the process, what we're trying to make happen in the process, so that we can know it's going to work or not work. Any questions? So this is where we make that decision. The only thing that we could be off by is a constant factor. I've got x squared dx, 3x squared dx. I can easily deal with that 3. We'll just divide both sides by 3. There are other ways of dealing with the dx, but they focus more on process than on knowing what's supposed to happen. We'll do that too, but probably won't get to it until Monday. We'll talk about an alternative to this to replace the x squared dx with 1/3 dw. It leaves these real awful looking mixed integrals with two different variables in there. Ugh. Let's look at an example where this is not going to work. Let's suppose I had the integral of x we're going to see fairly quickly that this is not a substitution problem. It's important that we be able to look at this and see why it is not a substitution problem. So the thinking is the same. The only thing that's a candidate for an inside function is an x cubed. So I'm going to make a substitution, w equal x cubed. If w is supposed to be x cubed, then for my dw, I'm going to need a 3x squared dx. And right now, I know the problem is somewhere for substitution. Substitution has failed me in this problem. Because what we need is an x squared dx, but I don't have enough x up here. I've only got one factor of x, and I need two factors of x. So I don't have an x squared in my original problem. So substitution is not going to work. We don't have x squared as a factor in our integral. We only have x. Specifically x to the first power. So this is not substitution. Since substitution is the only option that we have right now in our mathematical career, we are done. This is beyond what we can do with the problem. Any questions? Here's what some of you might be thinking. Well, in the previous one, you divided out this 3. What if you just divided out an x as well? Is anybody thinking that? It's okay if you were. That's good, because you're trying to make things go. That's really good, actually. It's very good to think, why don't I just divide out the x over here? Because it's demonstrating an understanding of what we want to happen in the problem. I want to replace this x and the dx with the dw. Here's why we can't just divide out an x. So we might think, well, I've seen lots of sports movies and I know nothing is impossible. We just need to have a rock and roll montage of training. I've adapted the rock and roll montage of training to class, to school. I have the whole thing in my mind. And it's really annoying because every time I bring that up, I start imagining the rock and roll montage. I imagine this whole thing as like a sports movie where everything's going to come down to the big test at the end. And I realize just how corrupted my mind has become by all the friggin' believe in yourself war stories. You know what I mean? So you might think before you just divided out the 3. What if you divide the x as well? And here's the problem. My expression 1 over 3x dw, that still has x in it. And the brief for substitution is all x must become w. And so that provides us with a problem. So at this point, we could substitute this in, but now not all x are w. We wouldn't have, this would leave x in our w integral. And unlike chocolate and peanut butter, these are not two great tastes that taste great together. We can't have x in our w integral. I don't know why I'm shouting every sentence today. And it's because when I'm standing up here teaching class, it feels like I'm shouting. So if we tried this strategy, I'd replace x and the dx with a 1 over 3x dw. But now my w integral still has x in it. And if I go back here and say, what if I just make x equal to cube root of w? Now I've created more problems. It's just going to make things worse. It's not that we can't do it. It's just that it doesn't help us. So doing this substitution down here, first of all, we'll realize that I wrote this too high, and I knew I was going to be doing this, so I don't know why I got so tall up here. Just angle that down. I should be able to copy and drag that anyway. What are you gonna do? So the x and the dx, if that becomes 1 over 3x, my outside function is still sine of x cubed. My x cubed becomes w. And the problem is I've still got x in my, oops, I put dx, I want it dw. So the problem here is I've still got x in my w integral. So there's a problem. We still have an x in our w integral. All x must become w. If we appeal to our original, w equals x cubed, maybe I can turn this into, say, x is equal to the cube root of w. So maybe you're like, oh, haha. You know, you didn't think of that, did you, smart guy? But you can tell by the way I'm saying this that it's not going to help us, because I'm being so condescending and dismissive. I apologize for that. I'm just trying to be silly. If you thought, well, I'll just make the x the cube root of w, that's an excellent thought to have. It's not going to make things work, but you're still focused on what we know we need to make happen. And that's good. Does that make sense? This is a perfect mistake to make. I'm just going to divide by the x2, and I'll put that back in. Oh, dang, there's still x in my w integral. Still focused on what we want to have happen, I will just turn this around and say x is a cube root of w, which is an excellent suggestion because you're still focused on what we are trying to make happen, an all w integral. The problem is the all w integral we end up with, I'm going to take out the 1/3. And then we'll have an integral. This 1 over x is going to be a 1 over cube root of w. So I'll have this sine of w That's not changing. And I'm going to put this x in the denominator, and I'm going to write it as a cube root of w. This is a perfectly valid substitution. We have gone from an x integral to a w integral. This is what we want to have happen. The only problem is we ended up at an integral that we also don't know. We don't have a technique for dealing with this integral. Technically we do, because we have Wolfram alpha right in our pockets. But that's not what we're trying to do. Otherwise, like, oh, welcome to Calc 2. Hey, Wolfram alpha exists. All right, everybody gets an A, on to Calc 3. So this is a valid W integral. But we still don't know how to integrate. This is a way more example than the first one. A way more important example than the first one, because the first one, everything worked out. I think too often in math class, we do all these examples that just work out. And I think we don't go far enough to things that might work. So I could have just stopped right here and said, we need to have just an x times dx, but we've got x squared dx. Substitution is not going to work. Let's move on. But we need to address people that are still focused on the goal. And like, I'll just divide out the 3x, the 3x as well. But then identifying this as being a problem. I can't have x's in my w integral. I'm trying to make a w integral over here. And then some of you, it's still going to be, well, hang on. If w is equal to x cubed, then x has to be the cube root of w. But then we get to an integral that we don't know how to do still. So it didn't work, still not substitution. What we're trying to develop is not just this method, but the instinct for knowing when things are not going to work. So that you can get to this point and say, oh, this substitution is not going to work. I'm going to have to do something else. And then starting on the new thing. Does that make sense? Remember the goal of the math class is to get so proficient at all the math that you don't need to do all the math anymore. Because the amount of writing that needs to go on in this one, if I say integrate by substitution, you're like, oh, that's not substitution, and just move on. The amount of writing that you need to do in the previous problem is to see the x squared sine of x cubed, not write any of this and just write the answer. That's the goal. Forget show your calculations or show all your work. Going from the beginning to the end is showing all your work. Because I want you to be able to just write down what the answer is. That's the goal. That make sense? Instead of having to think about and write down all the details, you want to get to the point where you can just write down the answer. So if it starts off here, you just write the answer. I say, but I said, show your work. You're like, well, I did. Because I can just write down the answer. You know what I mean? If I actually multiply 7 times 8, hopefully you'll come up with 50 something, 56. There's nothing to show there. That's something that I asked you to memorize. I didn't actually remember. I wasn't your elementary school teacher, but someone did in the past. Said you have to remember this. 7 times 8 is 56. Then I teach you about 2-digit multiplication, in particular, like stuff with zeros in it. Like if I say 70 times 8, it should just be 560. You should just. But if I'm like super fundamentalist about show your work and demand that you write 70 times 8 and have the 8 times 0 and the 8 times 7 is 56. I'm being insane. That is unhinged. That is completely not understanding the point of the exercise. The reason that we learn these things is so you don't have to write down 70 times 8. You know what's going to happen. It's 560. You know what that 0 is going to do. And then understand multiplication enough that when I say 71 times 8, it'll be 560 plus another 8, 568. You don't write things down. The whole point is to stop writing everything down. But right now we're learning, so we write everything down. Any questions? Comment? Yes. Oh, that's one that we didn't do, is it? The integral of an exponential function. We only did the e to the x function. So we should just add that. Let's add that to the list. So remember that the derivative of, say, a to the x is a to the x times the natural log of a. Here's where a is a constant and x is the variable. Note that we did do this on e to the x, but natural log of e is equal to 1, so we didn't write it. We can turn this around. Natural log of a is a constant. So when we turn this around, this is just a constant. So I can just divide both sides by the natural log of a, and we can integrate a to the x dx is a to the x divided by the natural log of a. Good question. I do remember forgetting to do that one. Any questions? How's everybody okay? One of the things that needs to be observed about me as an instructor is that I talk a lot. I was raised in a system where I stand up here and blah, 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 and you sit out there and write. So for good or ill, that's the habit that I've been building up over the career. And you may have noticed that I do tend to talk a lot. So if students ask about me, they need to know he will talk the whole friggin' time. You're like, well, he never shuts up. He never shuts up. This is exemplified by the fact that we just did an hour-long class. I did 2 examples, one of which wasn't working, didn't work. It's like 2 examples. So. That's the thing that needs to show up on the Rate My Professor site. Will talk forever, does not shut up. I'm gonna have to go in and put those reviews in myself. I'm gonna put in all kinds, I'm gonna give myself low rating. I want smaller classes. I'm gonna go in there and give myself a good rating. If you think that's incredibly manipulative, that's like how Yelp works. Every Yahoo has access to it. Some people might even use Yahoo to access it. Those are like old people. I have one of my friends, his email address is still Hotmail. It's like, what? A vintage email address. AOL. I wish I still had my AOL address. Vintage. I wonder if it'd be now cool to have an AOL address. You can catch my email at ecleach@aol.com. People are like, what? I thought AOL.com used carrier pigeons. It's like, oh, I need to send an email to Leach at AOL.com, and you like strap it to a pigeon's leg. Then I'm sitting in my office. Pigeon comes flapping through the door. It's like, an email. Any questions about substitution? I haven't assigned the substitution homework. So for those of you reading along in the book, integration by substitution happens in chapter 7. And you may be wondering, why are we going so fast through the book? The answer is because we can. And let's have more stuff to work on so that you learn how to separate all the things. One of the skills you have to have as a student is learn how to deal with being overwhelmed. So I got to overwhelm you right at the beginning. All right, that's it for today. That's it for this week. I'll see y'all on Monday. Everybody have a good weekend. Thanks for playing.